Welcome everyone to another webinar in our DYNAmore Express series, and today we talk about optimization. And the idea of this webinar is to give you an idea about what kind of tools can you use to perform either a topology optimization or a parameter optimization from the LS-T product line. And because usually we receive a couple of requests, okay, I have this optimization problem, what can I use? Yeah, and hopefully at the end of the day or after the webinar, you at least get an idea and you know, okay, for this one I need to use this tool, for this one I need to use this one. And I also want to give you an overview on what you can do with these tools and what is new in the latest features. So first of all, I give you a general overview about optimization strategies, and then we talk about LS-TaSC, and then of course LS-OPT. Okay, first of all, we need to classify optimization. Yeah, so in general, there are different things we can optimize. Yeah, we can optimize the topology of a structure. Yeah, the shape, the size, location of gaps. Is there a hole, no hole? Where's the material? Where's no material? Yeah, we can optimize the topometry. Yeah, so let's say we have already given a certain shape. Yeah, but we want to somehow fine adjust it a little bit. So let's say we have a structure, we have a beam with a certain thickness, and then maybe we adjust this thickness in locations. Yeah, a little bit. Yeah, we want to have at least a location. We need to have a thicker beam, or thicker shell, or thinner shell. Yeah, is one way. We can also adjust the shape. So let's say we have a curvature. Yeah, but what is the optimal radius of this curvature? Yeah, this is also a question. Yeah, this goes also into optimization strategies. Or if you have a given shape, yeah, you may also parameterize the shape. So let's say instead of having this free surface, yeah, we have many parameters. You may have just one parameter for the shape. So let's say a location of a so-called reference node, which changes the slope or whatever. Yeah, this is also some kind of optimization. Or you can do a size optimization. Yeah, you can, I don't know, make a cross section bigger or smaller, for instance. Yeah, of a beam. Yeah. Or, of course, and this is the most common application for, let's say, LS-OPT, yeah, is the material optimization. It means you're trying to match the parameters of a material model to best fit experimental data. And based on the optimization you want to do, yeah, you choose different products. And basically you can say that all the other part here, topology optimization, topometry, shape optimization, goes with LS-TaSC, and everything where you can parameterize your model. So it means you can somehow boil down the variable you want to adjust to a single parameter or a couple of parameters. Yeah, then you go with LS-OPT. Yeah, so LS-TaSC is so to say a topology optimizer. So you can identify where's material needed, where's no material needed, and LS-OPT is a parameter optimizer. So it's optimizing based on a parameter input. Yeah, but I think it comes more clear when we move on to the examples. Okay, here's again an overview about optimization strategies. Like I said, topology optimization. What does it actually mean? It basically means, okay, I have a design space, I have my load, I have my constraints, and now I want to know, okay, with this design space, yeah, where can I remove material, or where do I have to add material to match a certain design criteria? For instance, maximum stiffness with minimum weight. Yeah, then for instance, you end up with something like this here. Yeah, so you have holes here because you do not need so much material here. Yeah, or you add a more internal structure to it to increase the stiffness. Yeah, or here, this is an example for shape optimization. You already have a curvature here. Yeah, but you may adjust the curvature. You change it. You change the radius. You change the geometry of the curvature to find the optimal design. Yeah, or here sizing is another problem. Yeah, for instance, you have this cross-sectional area, yeah, as a block, and then how thick does it have to be? Yeah, or the same applies here. Yeah, for a hollow cross-section area, what's the thickness, the length? Yeah, or more complex shapes. Or of course, you can also optimize materials. Yeah, so for instance, if you have fiber reinforced plastics, what is the optimal stacking sequence of your layup? For instance, what's the fiber direction? Yeah, this is an optimization strategy. And depending what you want to do, yeah, some of these optimization criteria or techniques can be done with LS-TaSC because they are somehow, so to say, more freely, and other ones you need to parameterize your model first, and then you optimize these parameters. Yeah, so just keep in mind, whenever you have a parameter you want to, a specific parameter you want to optimize, could be 1, 2, 3, or as many as possible. You talk about parameter optimization, then you go to LS-OPT. If you want to find a shape or the if you have no idea, so to say, yeah, how the perfect geometry for your application looks like, then LS-TaSC is the way to go. Okay, let's take a look on LS-TaSC. Here we talk about topology optimization, and I said it already. LS-TaSC as a topology optimizer answers the question, what is the perfect geometry within this given design space to let's say, to match your optimization criteria. So for instance, in this case, I have my load here, I have a symmetry plane, I have my constraints here. So what is the best design, yeah, with maximum stiffness and lowest weight, for instance, yeah? And this is what LS-TaSC is doing. Yeah, so it's computing, iterating, and then finding the optimum design. And the whole procedure is based on the design variable. In this case, is a so-called relative density. That means you have a parameter applied to each density in each part of the model. Yeah, so each element has a certain density, and then you take away with design variables between 0 and 1. You adjust this design variable. If it's 0, then the density is 0, so there's no material. If it's 1, it's full material. And then based on the 0 and 1 optimization, you find a design. You're creating material where material is needed, and you remove the material where no material is needed. And by that, at the end of the day, you found the optimal design. Yeah, and then you can export this design and start working, redefine it using CAD geometry, and then, I don't know, take a look on it production-wise. Can I produce it like this or not? Yeah, but this is a really good approach. If you have a new part you need to create, you have these load cases, and LS-TaSC may give you a good, at least an idea how the design has to look like. Yeah, so it's a very good approach if you have a new part in your portfolio. So, okay, what can LS-TaSC handle? In general, it can handle, of course, nonlinear problems. Yeah, so it deals with dynamic loading, changing loading conditions. We can deal with contacts. We work with shells and solids, so it doesn't matter what you want to do. You can use shells or solids. We can use really huge models, 10 million elements, and we can also optimize different load cases at the same time. I have an example for that later on. And basically the criteria we want to do is we want to optimize two different constraints at the same time. So for instance, we want to assign, okay, I want to have a certain energy absorption. Yeah, I want to have maximum reaction forces as a limit to my constraints. Yeah, so the optimization is trying to achieve something, but I can also apply constraints to this one. Yeah, I don't know, acceleration has to be, I don't know, lower than a certain value, for instance, if I talk about impacts. Yeah, so this is also as a certain constraint. Yeah. Okay, what we also can take care of is some certain geometric properties like symmetry, of course this one here, or if you have to some kind of extrusion property of my geometry, like this one here, I can deal with castings, so I can, for instance, make sure that I have a certain thickness of my structure, one side and both sides. Yeah, I can work with patterns in the latest release version, but I'll get back to this later on. Yeah, so there are certain properties we can already invoke into the topology optimization procedure. Okay, how does it work? So basically, the topology optimization, the main criteria is the homogenization of the internal energy density. So internal energy is the energy, if we apply a load to a structure, and internal energy represents the energy which is stored inside of the structure. And by minimizing this energy, we somehow we try to achieve an equal stress distribution as equal as possible. And this is the perfect, so to say, the best objective you want for your optimal structure, right? So if you have a structure and you don't want to have a material where there's no material needed. Yeah, so we have low stresses, you take out the material, and the load then somehow transfers to the neighboring areas, and by that you somehow can design a structure which is, in the best case, has an equal stress distribution. Yeah, and the criteria we use here is the homogenization of the internal energy density. What we use here is the so-called projected subgradient method. This is an extension of the method, and with this one we can also perform impact statics and NVH optimization at the same time. Yeah, I'll get back to this in a minute. And of course, we also can optimize the free surface design. Yeah, and we want to have somehow uniform surface stress distribution. Okay, LS-TaSC is integrated very well with LS-DYNA because it's the same company, of course. Then we have a very well integration. So LS-TaSC, of course, works with LS-DYNA. So you perform LS-DYNA simulation within the iteration, in the optimization loop. Yeah, then LS-TaSC tells LS-DYNA what to do, what to optimize, what kind of model to analyze, and then they have this loop. LS-TaSC works also with LS-Prepost for the post-processing. There's also integration also for the pre-processing. Yeah, so let's say extracting results, or during the iteration, you may also take out the results, take curves from LS-Prepost, and then feed them back into LS-TaSC. And also LS-TaSC and LS-OPT work together, so we can perform design topology optimization together with a parameter optimization. Okay, let's move on to some application examples. So this is a very simple one. That's a connecting lug. We have a load here, we have a constraint here, and we want to find the optimal design in between the constraints. And the question is, can I reduce the stress concentration? So if I take the initial design with having a rectangular cross-section area, I do find in the simulation the stress concentration here. Yeah. So I can use this, run a topology optimization. So LS-OPT will remove and add material. And then at the end of the day, this is my optimal design. So LS-OPT will add material here in this area and take away material here. Yeah, because you have low stresses here. So we take away the material, we add material here, and then at the end of the day, we find this cross-section area. And overall, we do find a 20% stress reduction for this particular example. Yeah, so it can help you to improve your design if you already have a design available, or if you have no idea at all, so you start completely from scratch. Yeah, you just give the design space and just let LS-TaSC find you a more optimal design. So for instance, in this case, yeah, so there's a bottle opener. So this is the boundary value problem. This is the bottle top, obviously, that's the cap. This is the design space I'm prescribing. Yeah, so this one here goes my thumb. So just think of this one. I'm pushing down here, so this is my thumb. Goes here, my index finger goes here, so just putting up in this case. I have also contact here and here. And now the question is, what is the optimal design given a certain criteria? So in this case, we want to have the highest stiffness with the least weight, or the lowest weight. So this is my design space I'm giving, and then LS-DYNA is recomputing it, LS-OPT, sorry. LS-TaSC, LS-DYNA is recomputing it. Okay, identifying some areas where I don't need material at all. So it means the relative density goes down in this one, goes up in this one. And then after a couple of iterations, LS-TaSC is finding the optimal solution. Yeah. For instance, here you see the stress distribution. And of course, you can also extract isosurfaces from the structure, which you again feed into your CAD program to further redefine it with some, I don't know, production-wise constraints, so to say. Yeah. Next one is the B-pillar of a car in case of a side impact crash. And the objective here is we want to have the stiffest structure, obviously, because we want to protect the passengers. We want to minimize mass because we want to have a lightweight car. And of course, we have certain constraints we need to match as well. For instance, we have to restrict the displacement or the deformation of this B-pillar. Yeah, because we want to protect the passenger. And if the movement or the deflection is too high, yeah, then of course we will hit the passenger and then we injure the passenger. Yeah, so this is the objective: stiffest structure, minimal mass. Sorry, and we're going to satisfy the constraints of which is related to certain displacements. Yeah, and then we can run the performance, the optimization procedure with a given load case. And then this is what we find. So this is the initial design, some pretty broadly. This is our design space, yeah, so average. And then LS-DYNA or LS-TaSC is computing the relative density. And this tells us, okay, where we can remove material, where we can add material. And this is how the structure then looks like at the end of the day. Yeah. Another example is the hood of a car. Again, achievement, what we want to achieve is stiffest structure. We want to have satisfies constraints and minimize mass. So pretty much similar as before, but this time is a HUD. So we have different load cases, bending, torsion, and this one here. And again, we start with initial design. And so we first off setting up the structure and then removing again material, and this is what we're ending up with, and this is the optimal design. And what you see here on the color fringe plot here, you can see which structure inside of the old optimal design contributes to which load cases. So for instance, the green one is the torsion, the red one is the bending, and the blue one is the rear beam load case. Or another example, we have an automotive crash box. And again, we want to minimize the mass of a structure. The constraint is we want to have at least an energy absorption rate of bigger than 1 or equal to 1. And we want to compare this to a shell structure. So this is the reference shell structure. We compress the box, which is a box made of shells. So that's a hollow box, like a can, but just in a rectangular cross-section area. We compress it and we want to know, okay, what is the optimum design? So we want to minimize the mass. So first we start with the initial design. We make this as a solid block full of material. Then of course the mass is pretty high. So here we have 1.5 kilos. Here we have 23. We have a really high, the peak acceleration is really low. And now we want to optimize this structure using LS-OPT, so using topology optimization. And this is what we end up with. This is the structure, how it looks like. And if you compare the end result, you see that the mass is even lower than compared to the shell elements. So it's even smaller. We have the energy absorption of 1, and also the peak acceleration went down in comparison to the shell structure. So basically, with this again, shape optimization or topology optimization often gives us an idea on how a possible structure could look like if we want to achieve something. So you may consider some kind of inspiration for your designer. How does the shape has to look like? I think this is a good way to approach. If I don't know how the shape is supposed to look like, maybe I can run this kind of simulation and then see what is the computer proposing, or what is my objective proposing to the design. Again, this is the structure. So this is the evolution of the optimization. As you can see, it's taking away the material, and here we can compare how the shell and the solid compare in a crash simulation, and the result is pretty much similar. But again, the weight is lower compared to the shell structure. Now it's up to the production designers to make a shape which can be produced. But I think nowadays, 3D printers, it's possible to have complex shapes. And you can see that complex shapes are hard to manufacture, but often give a better result or better performance of your part in terms of the requirements. Next example is related to impact statics in GmbH. So what we're going to do here is now we're going to optimize a shape with a couple of load cases at the same time. So we have linear bending, we have an impact loading, and we have an eigenfrequency problem. And we want to match, we want to have a shape which matches criteria to different load cases. So this is the result. So the load is here. And if I take a look on this one here, I can clearly, now in this plot, I can clearly identify which part of the structure or which part of a design or which feature of the design matches which load case. For instance, so the blue part here is purely optimized for the eigenvalue problem, for the eigenfrequency problem. What else? So the dark green one is the pure bending load case. The blue one is the pure impact. And here the light green one is eigenfrequency plus bending, and the orange or brown is impact plus bending. But I think this kind of fringe plot is often really helpful to identify which part of the optimization or which load cases contributed to which design feature in my final structure. So can I get a feel for it? Okay, if I have this load case, then I get this feature. And sometimes it might be necessary that you say, okay, there's one feature which somehow makes my optimal design way worse than it's supposed to be. Then you may say, okay, then I don't take out this load case and proceed with another one. And then somehow find another way to somehow achieve what I want to achieve. But I think this plot is pretty helpful. Okay, what are new features in the 2022 R1 release? So the one which was released in January this year. Next release is in June, July So there's an R2 in this here also. Of course, there's an update in the detailed plot interface. Now the designs can be exported as STL, and as you know, STL is a geometric format for free surfaces. So it's pretty helpful. So you can go right into the CAD or go to your designer with your optimal design. And I think what's also important to point out is here is padding and cyclic repetition. So you now can use patterns to repeated structure and also work with these in your optimization procedure. Okay, that's it for LS-TaSC. Now let's move on to LS-OPT. What is LS-OPT? As I mentioned in the beginning, LS-OPT is a parameter optimizer. So that means every time you can somehow parameterize your model or what you want to design, what you want to change, you can use LS-OPT. That means you can add a parameter to the shell thickness. You can add a parameter to a nodal location. And if you can do this, then you can run it with LS-OPT and optimizing a design. And there's a couple of interfaces. Yeah, of course, there's an interface to LS-DYNA, but LS-OPT is not restricted to one tool. Yeah, it's a general optimizer. You can extract results from an abacus, from ANSYS. You can even have here some Python scripts. You can have MATLAB. You can have everything. Yeah, you just need to have. You have to define an input which matches a format, then goes into something. You may call it just a black box, and then comes out something which again LS-OPT understands. Yeah, so feed something in, LS-OPT can handle with. You get something out, LS-OPT can handle it, and then you can perform optimization with whatever you have. Yeah, and it could be an LS-DYNA simulation. Yeah, there are also more comprehensive interfaces to LS-Prepros, Primer, ANSA, Hypermorph. If you want to do a shape optimization, again, ANSA and these tools, they help you to parameterize a finite element model, and then you can also perform shape optimization. Not in the big range as, for instance, with LS-TaSC, but still you can do some design optimization. Let's say tweaking a little curve, yeah, tweaking something here a little bit, yeah, optimizing a curve a little bit, yeah. Not very general, but at least you can also do it here. You can use, there are some interfaces for the extraction of the results. So what is the displacement? What is the curve? Yeah, how do I get it out? And then to have this as an evaluation, how good your iteration in the optimization step was, yeah, and so on. And then of course you can have interface to LS-OPT, LS-TaSC. You can create some nested loops. Yeah, so you can optimize shape and parameters at the same time. Their user interfaces and so on. You also works with queuing systems of clusters and so on. Yeah, so on the right hand side here you see an overview, and this is actually how LS-OPT looks like, and it works in a more graphical way. Yeah, so you have setup, then they go here, you can design some, you can set up some parameters, how you want to optimize it, what kind of method you want to use, then you create your simulation, you run LS-DYNA, you extract in results, then you perform your optimization, and then you check, does it match your optimization criteria? If not, you go again. And then you go this loop until you find you match your optimization criteria, and you're out, and then you finish your optimization. And LS-OPT is pretty much designed around this graphical drag and drop interface. LS-OPT optimization, LS-OPT integration, LS-DYNA integration, as I mean, like I said before, it's you can use any tool which you want. Yeah, just feed something in, LS-OPT understands, you get something out, LS-OPT understands, and then you can perform optimization with anything. But of course, it's from the same company, from LST, so you have a good integration of LS-DYNA. Yeah. So for instance, you can right away extract results from the LS-DYNA results databases. Yeah, you don't have to create some intermediate scripting interfaces to extract the data you want to have. You can just access the data from LS-DYNA results right away. Yeah, so talking about bin-out files, for instance. Yeah, so it makes life way easier. You can work with include files, and so on. Here you can also monitor the process and so on. Yeah, so it's way easier to work with LS-DYNA, of course. So how does LS-OPT work? In general, they use what is called so-called response surface, and basically the idea is you within the design variable space. So what are the variables? You have some constraints, you compute some values and you compute a response to these values. And then you have a couple of points in your response. And then you use a so-called response surface. It means there are different ways of doing this one: polynomial functions, radial basis functions, feed-forward neural networks. So, and based on this response surface, which again is working with certain pre-computed values, you somehow work your way down the optimization strategy. Yeah, there's one way of doing this one. Is response surfaces. It's quite common. Another way is using genetic algorithms, and basically these algorithms mimicking evolution. That means variable states, variables, input variables, which give you the best fit to your objective, proceed further than mimicking evolution. Yeah, basically having orphans, offsprings, with some random mutations and so on. By this you can optimize also your strategy. Or you can perform a Monte Carlo simulation, yeah, for instance, for robustness analysis, if you wish. So there are different methodologies to do an optimization in LS-OPT. Another method is the so-called method of classifiers, and I'm not so much in the detail of this one. So I think my colleague Katharina Liebold, who's actually working with LS-OPT, and he's one of the developers, can say way more of this one. What I can add to this one is basically there are some problems where you have where your response function is not continuous. So we have some jumps in it. For instance, when you have buckling problems. So if you have a beam, you apply a load, and you get a certain buckling pattern. Yeah. Now you change something in the input. Let's say you adjust the material parameters, or you adjust something which actually happens during your optimization strategy. You may end up with a completely different result. Yeah. And this is somehow the branching problem. And when you have this branching problem at your response function, you would have had a so-called discontinuity. So some certain jump is certainly a sudden, completely different response. Yeah. So does the beam buckle in this way in one load case, and the other load case it buckles in a completely different direction by just adjusting the input parameters a little bit. Yeah. And then for that method, you have this methodology of classifiers, support vector classifications. To just let you know that there's a strategy to deal with these discontinuities. Okay, application of LS-OPT, I already said at the beginning, mainly whenever you can parameterize something in your model, you can use LS-OPT to optimize this specific parameters or these specific parameters. You have a kind of multi-objective optimization and so on. There are a couple of ways, but I go through this one now in the example session. The first example is the optimization of parameters. It's the very common, most common application, I would say, for LS-OPT. So what you have is you have a test curve, and you want to match your simulation model matching this test curve. And usually you do this by identifying the parameters in a material model. Yeah, you're adjusting elastic modulus, you're adjusting a Poisson's ratio, you're adjusting yield stress, and so on. And by these adjustments, you want to find what is the best fit to your experimental data. And of course, you can do this all by hand. You can run a simulation, you can extract the data points. For this displacement, I have this force, for this displacement, I have this force, and then use some error function, mean square error function, do it all by your hand, or you can already reuse an existing function in LS-OPT, which actually tells you, okay, I insert a target curve, so which is the test curve. This is my computed curve from the material model I want to fit, and then I just apply mean square error of this one, and then LS-DYNA basically does this all for you. Yeah, oops. Yeah, you can do this by hand, or you ask LS-OPT to do it by hand, so it's way faster. Yeah, that's one way. What we can do with parameter optimization is one. Yeah, here's an example of parameter optimization, which is called full field calibration. And the idea of this one is usually when you do a test, you have a tensile test, you measure the displacement and the force. So it means you have force and displacement, two values to match the material data. Yeah. However, if you have complex material models, you have a lot of parameters usually in the model. Yeah. And usually it helps the more test curves you have, the better you can fit to experimental data. Yeah. Because you're somehow trying to balance certain fluctuations. Yeah. And full field calibration helps with that. So what you do is you create a tensile test, you have this sprinkling pattern on your tensile specimen, and then through digital image correlation, DIC, you're trying to compute a strain field based on the movement of this sprinkling pattern. Yeah. And then, of course, it means that you have not only stress And you not only have force and displacement, you also have a whole strain field. Yeah, that's why it's called full field calibration, because you have the full strain field and you're trying to match in your simulation the full strain field. And this is what the guys in our lab are doing, and usually you achieve way better results using this full field calibration. Yeah, if you're interested, feel free to contact us. Our MCC, our Material Competence Center, is working with this one. What you also can do is so-called sensitivity analysis. So basically answering the question, if I have a structure and I want to know how sensitive is the response to a certain input. So let's say, how sensitive is the head acceleration in a car crash to the thickness of a crash beam, for instance, yeah, the size or the geometry or the thickness of the shell in a crash beam. How sensitive is the head acceleration? And then this is often also helpful to give you an idea what kind of material or what kind of, if you want to improve your model, your product, what is the best point or where do I start? Yeah, for instance, in this case, I don't know what this simulation down here was, but from this simulation you can see that the yield stress in the material model has the most effect on the outcome of the result. So that means, let's say you want to improve your model, yeah, that makes more sense to somehow work with the yield stress of the material. Yeah, so it means maybe replacing your material with something else, yeah, with a higher yield stress, yeah, to get a better product. Yeah, and you can also see here that the friction values, they don't do so much. Yeah, the most part goes into the yield stress. Yeah, so this gives you the idea of where to start improving your product. I think this is pretty helpful. Next one is the stochastic probabilistic analysis. So the question is, when you have a structure, and usually any real material is does have some fluctuation in the properties. Yeah, so let's say not every steel produced from one manufacturer does have the same properties. There are some fluctuations in it. Or if you have a sheet metal, so the thickness of the sheet metal is changing. It's not always the thickness you want to have. And the question is, if I have a certain probability in the change of my input parameters, what's the outcome or the probability of the probability distribution of the outcome? So you feed some probability in and you get some probability out. Yeah, also really helpful, yeah, to somehow cope with uncertainties in your input parameters, sheet metal thickness, material properties, and so on. Yeah, so you can deal with this one. Yeah, for instance, let's say you have a sheet metal and your supplier tells you, okay, it's not 1 millimeter all the time, it's maybe 1.1 or 0.95, and if you take this sheet metal with a higher range of fluctuation, yeah, if you take this material and make you a lower price, then maybe at the end of the day you can save money because you're also accepting this lower price value because you know that the outcome of your result is not fluctuating so much with this change of parameter. Yeah, so this actually helps. Next one goes in the same direction, is robust parameter design, RDO. And here you want to know, okay, how robust is my outcome, again, with the fluctuation in the input. Yeah, how do I get the same result? Yeah, or how likely is it to get the same result with a fluctuation in the input? Yeah, let's talk about a few features. LS-OPT, yeah, and since LS took over, there's quite a few changes to this one. Of course, LS-OPT development goes on, but I think the most important part is first of all the release intervals. So there will be 2 releases every year, R1, R2. And the first R1 release was in 2022. The next one will be probably June, July. But I think the most important part is this one here. Yeah, so LS-OPT is now part of this optimization portfolio of ANSYS, and OptiSlang is the premier and enterprise optimization tool, and LS-OPT is part of the Pro, and I don't know when, but soon it will cost an extra license. Till now, it was for free. It was part of the LS-DYNA portfolio, yeah, but it will be cost starting since it is integrated into this optimization tier of ANSYS. What I want to point out is one of the most important updates is the so-called meta model of optimal prognosis. And basically, remember what I told you before, when you do optimization, you have to somehow, when you're working with response functions, you have to somehow decide what kind of model you use for the response function, polynomial, feed-forward neural network, and so on and so on. And for this, you need this experience. So what is good for this application and what's for this one? And this meta model, optimal prognosis, MOP, yeah, tries to take it away from you. So LS-OPT will design on its own what is the optimal one for your specific optimization. Yeah. So right now we have linear, quadratic kringing, and I think next soon also feed-forward neural network will be implemented, and then LS-OPT is choosing it on its own. So basically it makes your life as a user more easy. Also, the plot interface was updated. And I think what's really important to note is now it's possible to extract values or interpolate values between nodes. So if you have a simulation and this simulation is performed using finite elements, then you have nodes. And usually you just have values at the nodal locations. Yeah, and you have stresses inside of elements. But what happens if you have a test data somewhere located, not exactly at the nodal locations, but somewhere else? Then you need to interpolate this one. Yeah, before it was like you're just using the closest one, but now they're also using interpolation to match exactly the location of your test data. Yeah, so that's pretty much good enhancement, I would say. So, and this mainly used for full field calibration data. Yeah. Another extension is the Cora Plus interface. I'm not much into it. I don't know exactly what it is, but it's just something to do with dummy modeling, yeah, crash dummies. If you are into this field, probably you know Cora, and you probably now also know what to do with this. Okay, with that being said, I'm at the end of this webinar. Hopefully I was able to somehow give you an idea about, first of all, topology optimization and parameter optimization, give you examples, what you can do with LS-OPT, LS-TaSC, and hopefully it somehow clarifies a little bit the confusion which we often have, which tool to use for which application. If you want to know more, yeah, check out our DYNAlook, Dyna examples, for examples, Dyna support. And if you want to talking about LS-OPT, you can go to LS-OPT support. Also there you find manuals, you find examples, you find a lot of stuff, and the same applies also here. Also for LS-TaSC, you go to LS-OPT support. And yeah, with that being said, thank you for your attention, and see you next time. Thank you and goodbye.